I'm going to do the formation lap, and then I'll be handing over to our speaker for this F1 aerodynamics talk this evening. I've been handed a script, so I've got a few announcements after the lecture, so that's something to look forward to. Alpine, we've got the car outside, road car, Alpine road car outside, if you want to look at that, if you haven't done so already. For those old enough and brave enough to admit to watching Howard's Way in the 1980s, there was the Renault Alpine GTA in that. This is a little bit better, perhaps, but it's certainly worth a look outside. So I'm going to hand over. Very excited for this talk. You look very excited. Do we have any McLaren fans in this evening? Just one, but let's stick with Alpine for this evening, please, guys. Here we go.
Thank you. Good evening. My name is Jeroen Geltink. I'm Deputy Principal Aerodynamics for the Alpine Formula 1 team. I've been with the team for 14 years. And yeah, thank you for inviting me. I was asked to do a talk about Formula 1 aerodynamics. And I'm also glad to see the society reached out to some younger people, because I'm hoping to inspire some people to pursue a career in engineering. I've really enjoyed the last 14 years of my career in F1, and before that at Ferrari road cars, and I would highly recommend it to anyone as a line of work. But first, trying to wake you up with a sleek marketing video. So hopefully that gives you a bit of a better idea who we are. This is a picture of our factory in the lovely Cotswolds, about 45 minutes from here, not that far from here in Enstone. I'll give you a quick introduction into our team, into Formula 1 in general, then I'll tell you a bit about Formula 1 aerodynamics, delve a little bit deeper into the tools we use for our aerodynamic development. And last, I tell you a bit about my role with the team and the journey to get into Formula 1. And then there'll be hopefully loads of time for some questions afterwards. So first of all, our team, well, this is our car, A524 on the right, and our drivers, Esteban Ocon, the tall one, and Pierre Gasly, who are currently driving for us and almost crashed into each other last weekend. And you might not be so familiar with the Alpine F1 team, but actually we've been around a long time, but under different names, different guises. So it started off as Toleman, and we were actually based in Whitney, in my hometown, and then moved to our current site in Enstone, in the Benetton. Quite successful to driver championships and the constructor championship. That then became the Renault Formula 1 team and won another couple of prizes there to constructors and to drivers. And then that's when I joined at the end of the Renault era. And then we became the Lotus Formula 1 team. So we went private. We're quite successful then as well. No championships, unfortunately, but also it was the time where somebody made a joke: if you want to be a millionaire in F1, you have to start as a billionaire. It was very expensive. We ran out of money, and then so 5 years later, Renault bought us again, and we became Renault Sport, and that then turned into Alpine. Alpine is owned by Renault as a brand, and we're using the Formula 1 as a platform to market the brand and our cars. These are some of the drivers that have driven with our team. Anybody recognizes anyone? Nobody, some names. Stella, Alonso are here. Yeah. Ricardo, Schumacher, yeah. It was actually really nice touch with Senna. So we got an email, I think it was 2 weeks ago, to go into the race bay, everyone, because there was a surprise. They called it a blast from the past. And we were all standing around there. And then Pierre Gasly drove Senna's old car, the Toleman from 1984, into the factory. A lot of noise. The smell was pretty terrible as well. And he actually been racing there around Silverstone for a feature for Sky. And so that was made 40 years ago, the same kind of place, factory. And 6 people were still there that worked on the car. And they were actually quite emotional seeing it together again and obviously racing again. So it was a really nice touch to motivate all of us. So we are what you call a manufacturing team in Formula One. We've got Renault as a manufacturer behind us, and we build our own engine as well. Not all teams do. And so we got 2 headquarters, one in Viry, just south of Paris. About 400 people work there, all about the engine. And then everything else is in Enstone, and we're now about 1,000 people. We've grown a lot. So what happens in Enstone is more or less almost everything, but a lot of it is we make 95% of the car ourselves. We want to be in control of the production and the timeline and everything. So there's a lot of composites, obviously aerodynamics that are working. Our wind tunnel is in Enstone as well. We produce our own gearbox. The whole integration of the powertrain, suspension, vehicle dynamics, everything we do in Enstone. And then in Viry, we do the engine, which is the internal combustion engine, but also very complicated hybrid system at the moment. So Formula One is the most efficient fuel petrol engines in the world at the moment. More than 50% of the energy in the petrol is used to drive the cars. That has all to do with the rules. So we're trying to be relevant for road cars, and our fuel flow is restricted, and the amount of fuel we can take is restricted. So to win the races, you just need to be as efficient as possible with the energy. Obviously, the race team that traveled the world, 24 races this year, and test is there too. So our car consists of 26,000 parts, and it's about 3 or 4 million to build. You think that's expensive? For Formula One, that's peanuts. The R&D that goes into it is hundreds of millions every year. So it's a really expensive piece of kit. We only build 2 a year, and more or less everything changes every year again. You want to keep on developing, keep on progressing. The chassis, so anything that's gray, suspension, all the aerodynamics parts, but also safety system, crash noses, and all that. 55% of the parts. The gearbox, quite complicated as well, because it's load carrying and the whole suspension is connected to it. So it's not just the gearbox, 5% of the parts. The engine packaging, pretty big parts, but it's not a lot of it, only 1%, the red part. And the power unit, as I said, a very complicated power unit. So almost 40% of the parts of the car are in the power unit. Then a question I get a lot, and I'm always a little bit offended by it. Why do all the cars look the same? Because to me, they don't look the same. I know every little detail on every car, particularly in my area, the front wing. But this is the reason why. So the FIA regulates the sport. We are in the sport, so there's loads of rules. And there's about 180 pages of rules. If you ever struggle to sleep, you can just go to the website and download it. But yeah, it's very complicated. I literally had a discussion today with 3 people for about 20 minutes. And I still don't know if it's legal or illegal with the rules. It's definitely in the gray area. That's what I know for sure. But yeah. Here you can see what we call the legality boxes. So those are the boxes that the car can be in. And as you can see, that defines the shape. You can see the front wing there. You can see, I don't know if you see my cursor, but you can see the rear wing end plate, for example. So that's why the cars look the same, because they need to comply with the same rules. And they need to fit in the same boxes. Right. So what do we do? Well, we design, build, and develop and race 2 race cars with one goal, which is winning the Formula One World Championship. What we've got in Enstone is more or less any job you can think of. We're that big with 1,000 people, but we have a huge engineering office with loads of engineers in there who are responsible for the design and development of our car. There's obviously aerodynamics with our wind tunnel, with our supercomputer, our computational fluid dynamics, CFD analysis. But as you can imagine, getting those 26,000 parts all together at the right time to go racing is a lot of planning involved. Purchasing of raw materials and anything we get external, that all needs to come together at the right time. So we've got a lot of people working in that as well. You've got a lot of modeling, the strategy of any VPG, vehicle performance. So we've got a lot of people that are good at that as well. And as you can imagine, human resource, marketing, IT, pretty big department as well, because we use a lot of computers. So if you want a job in F1, you don't necessarily need to be an engineer. If you're passionate, we got a lot of positions and we're always looking for people. So done some facts about Formula One, because there's not really any country in the world where Formula One is the biggest sport. But globally, it's absolutely huge, and not everybody always recognizes that or knows that. So Formula One is owned by Liberty Media, privately owned. It's the most valuable sports empire in the world, bigger than some of them that own Premier League teams, American football teams, things like that. Race attendance in 2022, 5.7 million people went to the races. And then our average audience for Grand Prix is 70 million. To put that into perspective, they call it the biggest show on earth. The Super Bowl, less viewings. And you can imagine, if there's a final where Lewis Hamilton and Max Verstappen are equal in points in Abu Dhabi, it's about, I think it was over 200 million people watched that. And the only yearly sports event that has more viewers is the Champions League final than Formula One. So that kind of explains why there's so much money involved with it, and why you put so much work into getting these cars to race every other weekend. Right, that's a lot of words and a lot of text, but I quite like to show this video, which I think shows quite nicely how much is involved, and it also gives you a little bit of an insight into our factory. It was from when we were called Renault, so it's a little bit older, and it's pretty obvious that it's from our sponsor Microsoft, as you can probably hear, but I still think it's a nice one to share.
What people tend to forget in Formula One is that it takes in excess of 1,000 people to design, build, and operate two of the fastest racing cars in the world. It's all about collaboration and data produced by everyone. This year, we are going to experience a major change in the regulation. Every single part of the car is roughly composed of 20,000 parts, will be new. But that's normal. It's all cool. Everyone's cool because everyone knows what they have to do thanks to the experience, but also the software that supports this organization. This is where Microsoft is helping.
We started making parts for the new car before that season had finished. The pressure's really on us to deliver. We can have parts that are design release a day before they're needed, and they need to go give up the car goes to fire up.
It's very important here that we get manufacturing processes as streamlined as they possibly can. That has been the main area of focus for business intelligence. The introduction of Power BI and the products from Microsoft will have an impact on the car and the ultimate performance.
Data is critical to F1. Without it, we wouldn't understand how the car's performing, and we wouldn't be able to do the simulations to prepare for the season ahead. Formula One is very strict. We can't just build a car to any spec we want. Things like the amount of processing we're allowed to do and the number of hours we can run the wind tunnel are dictated by regulation. We see this as a way that we have to innovate to be able to get a competitive advantage.
There's 20 races this year.
searching up railway races. When you're the other side of the world, time zone's the biggest problem. You have to communicate on a platform where people can see the information when you're asleep and people can see their information when they're asleep. While the cars are going around the track, over 200 sensors are sending back a constant stream of time series data. Having our data stored in the cloud means we can access it wherever we are, but we have to make sure that our data is protected. And we know the Microsoft Cloud is only accessible by the people we want to access it.
What is very unique in Formula One is that the result of a work is measured against competitor every other week, and it's not everyone. We cannot negotiate on deadline. We cannot negotiate on budgets. Everyone has to work against the clock. You have to be ready for when the light out.
So hopefully that gives you a bit of a better idea about our team and Formula One in general. Sorry. So let's move on to aerodynamics. I don't know if can you see my cursor or not? Yes, excellent. So why is aerodynamics important? Because it's actually the most important performance differentiator in F1, so it's the most important bit to make the cars quicker. I think this kind of illustrates it. You got two cars here, both were designed with aerodynamics in mind. So one in the 1950s, beautiful car on the left, and then we got our race-winning car from a couple of years ago on the right. So the big difference between the cars is the older one, the one from the 50s, the only thing we care about drag less than we care about downforce. So it's all about squashing the car on the track to get the most grip. And to illustrate that, so this is the Indianapolis Oval track in the States, and that's the same track now as it was 100 years ago. So you can compare the lap times, so the average lap record over here. And as you can see, when they started racing there, the average was maybe 90 miles an hour. And they quickly went a lot faster, more powerful engines, things like that. And they climbed up to maybe 140. And then in 15 years following, it slightly climbed to maybe 150 miles an hour. And then in the mid-60s, it suddenly goes in 15 years from 150 miles an hour, the average, to 200 miles an hour. So in 15 years, it goes 50 miles an hour quicker. And that's downforce for you. So that's when they realized if we actually use downforce, we get more grip in the corner and we can go a lot faster. Then obviously the classic fight with the regulator starts, because they start to clip your wings because it becomes dangerous. So it didn't go as steep as that anymore later. So what is this downforce? Well, it's the opposite of lift. Trust me, this is the only complicated slide I will show you tonight. But it's all about Bernoulli's equation. And we're dealing here with low-speed aerodynamics. Obviously, you think Formula One car, 200 miles an hour, pretty fast. But actually, it's nothing compared to a fighter jet or the Concorde or a plane like that. That's high-speed aerodynamics. These cars are what we call low-speed aerodynamics, which means we don't really need to deal with anything that happens when you go the speed of sound. And then Bernoulli derived this equation, which is all has to do with conservation of energy. So he said that the pressure energy in the airflow plus the kinetic energy and the potential energy is always constant. Well, the potential energy doesn't change if we don't change the air, which we don't really do in Formula One. So it says the pressure energy and the kinetic energy together is always constant. So if you go faster, which is what happens here, like think about your garden hose, you put your thumb on it, the water will come out a lot faster. That's exactly what happens here. So we go faster, so the kinetic energy becomes a lot more. That means the pressure energy must become less. There's lower pressure there. So if we then look at an airfoil here, and we follow these what we call streamlines. So if you look at the one on the top and the one at the bottom, and they meet again at the back, then the one on the top has to go a lot faster because it has further to travel to get to the back than the one on the bottom. And now we know if it goes faster, pressure must be lower at the top than at the bottom. And that's why you can fly on your holidays away. And that's what we use in Formula One, but upside down. So I like to always do a little experiment with people. You can use your lap or the table in front of you, but why this works is if you just get your hand and you move it around, it's very easy to do. If you start pushing down on it, it's suddenly a lot harder. So that same hand has suddenly a lot more grip. And that's exactly what we do with the tires. We really squash them down on the surface. They get a lot more grip. And if you have more grip, you might win a trophy on a Sunday. So now I thought I'll break it up a little bit with a question, because this question has been going around for ages. And the question is, do we actually create enough downforce that a Formula One car can drive upside down? So we know it's related to the speed squared. I can't tell you our lift coefficient of our car, that's highly classified. You have to trust me, but with a show of hands here, who thinks a Formula One car can drive upside down? What speed? Well, within the 200 miles an hour it can do. So it's about a third who thinks it can do it. Well, I did the calculations. Our car can drive upside down with 110 miles an hour. So it is possible. And actually, I Googled it, and there's a company trying to get funding, I believe, to actually prove this, which would be handy because then I don't need to answer the question every time. But as you can imagine, it's going to be pretty challenging to go that fast and then smoothly go upside down for quite a while. But yeah, hopefully they succeed, and I can show a video next time.
Yeah.
So where does our downforce come from? So about a quarter of the downforce, 25%, comes from the front wing. That's the bit that I look after for our team. Then half of it is all from the floor and the diffuser, which is very frustrating because you can't actually see what's happening with the other teams. So we're always delighted when somebody crashes with a new floor like Norris in the last day, and it gets trained up in the air. And then 15% comes from the rear wing. And yeah, any of you clever people quickly calculated that's not 100%, and that's correct. So all the little flicks around the rear wheels and everywhere else in the car, they account for about 10% of downforce. And these are the tools we use to develop our car aerodynamically. So we've got computational fluid dynamics, CFD. We got our own on-site wind tunnel. We do track testing with a lot of sensors and brakes and things like that. And we got a simulator on site. I'll go into the tools in a bit, but first a bit our design kind of process. So we start here on the left with a new idea. So I don't know, somebody drove into work and suddenly thought, wait a minute, let's try this. What we first have to do, we need to put that in CAD. We need to put that in the computer, and it's just the surface. It's just the outer shape. We don't really care what's underneath it or if it can be made, anything like that. Then we put that in CFD, and then here you see it's a sport because we're very regulated what we can do in CFD. We can do about 225 different geometries a week. That quite often you do a few loops because it never works immediately. So you improve it, you go back to your CAD, back to CFD, and then you go, wait a minute, this is good enough. We'll send it to the wind tunnel. It then will be made. So we actually have designers that turn my surface with no thickness, nothing, into an actual part. Most of those parts are rapid prototyping. So we've got a big manufacturing department making those, and they will then go in the wind tunnel. Yet again, wind tunnel, very restricted. We can do about 30 different geometries a week. That's what we're allowed to do by the FIA. Quite often, that needs another iteration as well. So you need to go back to the CFD. Maybe it's not good at all, or it's it's okay, but it's not really good enough yet to go to the track. So you go back to the drawing board, you do again your CAT and CFD, and then after maybe 2 or 3 iterations, you go, yeah, that will make the race car quicker. It then gets sent to the design and production, so the design office, and they'll turn it into an actual car part that is light enough, and that also can withstand all the things it sees at the track, which is quite a harsh environment, as you can imagine. Then it gets sent to the race car. That sounds maybe complicated, but it actually can be really quick, and that's why I love that in the one. I think once I had an idea, and 3 weeks later I saw it live on television, so it's really cool. What's really important, and even more so now we're very restricted, is the correlation between our tools. As you can imagine, if you see something in CFD, it looks absolutely amazing, you put all that work in, it goes in the wind tunnel, it's not working at all, that's a problem, because you spent all that resource, you spent your CFD runs, you spent your wind tunnel runs, and you have nothing to show for it. What's even worse, if it goes to the track, it's better in the tunnel, and then at the track, it doesn't work, it's actually making the race car slower. That is a really big problem, because by the time because the track is always weeks behind what's actually happening, you've been developing CFD with it for weeks, in the tunnel for weeks as well. So yeah, it could really take you down a path where nobody wants to be. So we put a lot of work into our correlation to make sure our tools, when it's better in CFD, we know it works in the tunnel, and when it works in the tunnel, it definitely works at the track. So a lot of work goes into that, and it's really quite important. Right, I'll go into our tools a little bit more. So first of all, CFD. So the tool we use most. How does it work? Well, unfortunately, we can't actually solve the aerodynamics. So the Navier-Stokes equation hasn't been solved yet. If you know how to solve it, please do. Plus, you can collect $1 million, because that's the American Association has a prize on that. So that would make all our lives easier, but unfortunately, we can't do that. So what we do, we chop the air into tiny little cubes, about 200 million of them, and then we calculate in each cube what's happening, and that then has an effect on the next cube, and the next, and the next, and you iterate that until it's kind of stable, and then you go, right, that's our solution. So it's quite a computational heavy process, and then we can post-process it, and that's really where CFD is incredibly strong. I'll actually show you, because you can see everything. Normally you can't see air, so you don't always know what's happening. But in CFD, you can interrogate it all. So this is, for example, showing me the energy that's in the air, and I just slice it through the car, and I know exactly what's happening everywhere. So I can explain why something works, why something doesn't work. This is the surface flow on the surface. So it kind of shows me the health of the surface, if there's anything separating, if anything is about to go wrong. So I can look at that. These are the streamlines. So for example, sometimes you see something going wrong in the back, but it actually turns out that the junction of the front wing and the nose, there's something going wrong, but the loss of that ends up all the way at the back. But with CFD, you can actually trace that. So that's really quite powerful. It also shows you how complicated Formula One aerodynamics is. Incredibly unsteady flow around the car. These open wheels might look lovely, and the fact that you can see the driver, but it's a huge problem. The Alpine outside would be a lot easier to work on than this Formula One car. As you can see, it's an absolute mess. And that makes it really challenging, but also for the CFD solver to solve it, because the wheels are rotating, they're changing shape, all of that. So yeah, correlation can be challenging at times. The other thing we use CFD a lot for is to analyze all our heat management on the car. So unfortunately, we're not allowed any active aero components, which also means we can't have any fans or anything on the car. So normally your road car, when you stop, you hear the fan blowing to cool everything down. We don't have that. Thanks to this Brabham here, which said they had a fan to cool the engine, but it was actually to extract the flow out of the floor and the diffuser. It worked really well, but the FAA was like, well, this is gonna open up a whole can of worms and it's gonna be incredible difficult to police. So we just banned any active aerodynamics. And that's why you see when you see a car suddenly stop at the track, you know, when it's like, oh, stop the car now, within no time, things around the brakes, around the engine all start smoking and catching fire because nothing is cooling it down. And also when the car comes in the pits, you see a whole crew jumping on it with leaf blowers and things like that. That's all to cool it down. So yeah, we use passive cooling, just the airflow. This is the inlet duct on the front brake. And we have all kinds of ducts in there to cool the disc, but also the caliper and everything else. Obviously battery packs inside. The engine itself has radiators, things like that. And that all is done in CFD and not in the wind tunnel. This is our own CFD center, Teletubbyland, where we got our supercomputer. When I started in F1, if any F1 team got a new supercomputer, it would be in the top 10 of supercomputers in the world. That's not the case anymore because we're heavily restricted. The cost got out of hand, and actually the FIA said this is getting ridiculous. Teams are going bankrupt. So the amount of computational power we can use, we call it MAUI, is restricted. What that means is we do less CFD than in the past, but also we need to really think about how we do our CFD. So the most complicated simulations, the unsteady ones, are really computational heavy. So do you do one of those, or do you do 50 simple computations and then use an aerodynamicist to interpret it? Because we kind of know where the simulation will struggle. So we quite often choose quantity over quality, but that makes it quite challenging in terms of correlation for CFD to the wind tunnel. To show you how restricted it is, so when I started, well, it's actually a few years later, but we did about 30,000 CFD runs before the car would hit the track. 3 years later, that was halved. And I think we're now doing about 11,000 CFD runs. So it has got a lot less. Oh. Then a little interlude. You know about CFD now, so let's see if somebody knows this. But the question is, why do Formula One cars have such a tiny, ridiculous little windscreen here? You can barely see it. It's so small, it's definitely not to keep our driver dry in the rain. So here I got the CFD. I dug it out without windscreen and with windscreen. It's from a few years ago. But it shows you the principle, and then at the back you see the energy in the flow, and then on the surface you can see the surface pressures. So if it's blue, it's suctioned. If red, then it's a high pressure. And here you see the delta. Anybody has an idea why do we have such a windscreen?
Is it to create suction out of where the driver's sitting to keep them cool?
It's not to keep the driver cool, but it does have to do with the driver actually.
Is it to throw the air over the helmet?
It has to do with the helmet, indeed.
His visor clean.
No.
Actually manageable, right?
Sorry? Yeah.
To stop the buffeting around his helmet.
It's not the buffeting. It's actually
Is
where you
the
get
air
close.
clear into the airbox?
No, not to get the air in the air. It has to do with helmet lift. So you can see here, there's actually suction. The air goes faster over the helmet. So there's suction there. The helmet wants to take off. And you can see when you've got your little windscreen here, there's less suction there. So I think it reduces about 50% the helmet lift. Unfortunately, as you also can see from the black, it's not very nice aerodynamically. So in Formula One, there's a forever battle between aerodynamicists and drivers about the size of the windscreen, which is pretty ridiculous because it's maybe, what's it worth? Maybe hundredths of a second or something like that to fit it. But we don't like it. The drivers complain about it. Yeah, you get, so drivers have a spoiler at the back as well for similar reasons. So yeah, you can also we get involved with that because that can influence the cooling of the car, for example. So yeah, and to be honest, I was lucky enough, a few years ago we had Palmer driving for us, and I won the sweepstake of some others, and I was invited to one of his family's tracks to drive a lot of fast cars around, and that was the first time I drove an open wheel car, and the helmet lift it was really terrible, like the strap under your chin, and you felt like the thing wanted to pull your head off your body. So I'm a bit more sympathetic now, I think. So our second tool is the wind tunnel, and this is our on-site wind tunnel. We got a closed loop wind tunnel, so it's all ducted. So here is the fan that accelerates the flow. Then, as you now know from Bernoulli, because it gets bigger, it slows down initially, goes through the screens, and then just before our test section here, it gets accelerated, so we get really high quality flow over our model. That texture section maybe looks small in the picture, but this is inside it. It's really huge. You can stand in it with a lot of people. And there's where we have a 60% model of our car. And I actually found a video of it running. This is a few years ago, obviously, again. Because, yeah, I don't want to show you our current tunnel. But as you can see, we have a rolling road underneath the model, and that's because in reality the race car will go forward, obviously, and the track is stationary, but here the model is stationary, so the track needs to move, because else you get a boundary layer buildup on that surface, and with anything that's very close to the ground, you don't get a good simulation of it. So that's why all the Formula 1 teams have this belt running quite fast underneath the model. As you can see, we also get from Pirelli mini tires. So they give us 60% tires of the real ones. And then we got all kinds of systems to operate the model. So you can see a yaw in a little bit. So there's simulating a corner or a bit of crosswind. And it can steer as well. So you can really simulate what's happening at the track with it. It's still not as accurate as CFD, because our race cars, they burn through a set of tires in 20 minutes, half an hour. We can't afford that in the wind tunnel. So as you can see in this case, we have a smooth surface underneath, so they don't wear out as much, which also means they don't actually deform as much as the race tires. So it's much better than CFD, but it's still a simulation of what's really happening at the track. So then a little bit about our wind tunnel map. So a wind tunnel map is kind of the secret sauce of the team. It's where you put your emphasis in developing the car. And to show you that, I'll just go through a simple example. We go at the end of the straight, very fast straight, and we go through one corner. And on the y-axis, we have the front right side of the car, and on the x-axis is the rear right side of the car. So when we're in the end of straight, we're going really fast, and as we know, the downforce is connected to speed squared, so we've got a lot of downforce on. So that whole car is squashed to the track. That's when you see the sparks flying on telly, and we're really low down in both front right height and rear right height. Then we slam on the brakes, which means, as you know, in your own car, when you slam on the brakes, you fly a bit forward, so the front comes down a bit, the rear comes up, and then we scrub all that speed of the car until we hit the apex of the corner, which is the slowest bit. By that point, we don't have a lot of downforce on the car, so we're quite high up. Rear right height, front right height is all quite high. And then we accelerate. So what happens is the car kind of goes a bit on its rear axle, so the rear right height reduces, front right height comes up, and then we go through all of that again. So what you get is kind of a potato shape of all the front and rear right heights the car sees. And then what happens is with the wind tunnel map is that every team does tests a bit of a different bit inside the potato, and also will maybe emphasize a different bit. That's why you see some teams are good in high-speed corners, other teams are good in low-speed corners. And that's why you see the competitive order kind of changing with teams throughout the season. And it all has to do with their secret sauce, their wind tunnel map, what they do with that. This is just 2D. Obviously, we've got the yaw, we've got the roll, we've got the steer, we've got the exhaust blowing. So it's all a multi-dimensional space, and it's quite a complicated thing to navigate through, and always good topic for discussion amongst aerodynamicists. Then another thing that I already mentioned is our rapid prototyping. When I started doing these presentations, people were absolutely amazed by it, but now everybody has seen a 3D printer or maybe even got one. But yeah, we've been using these kind of 3D printers, rapid prototyping, for 2 decades now. And it's really an amazing kind of tool to be able to test all the aerodynamic parts in the wind tunnel really quickly. So here, this was the Manor wind tunnel model when it was for sale, and they actually hadn't painted the parts. So anything white is rapid prototyping. And as you can see, it's a bit like Lego. You can change all the little bits, you can test them. And here you can see as well, you just got a row of, I don't know, 4 or 5 different options that come out of the machine. And it had made the shape of the cars really a lot different, a lot more complicated. Because in the early 2000s, there was button in one of our cars. All the parts had to be made by hand, by people. And, you know, you can see the shapes had to be a lot more simple than the kind of 3D stuff we got now. So it really has helped us to really explore the aerodynamics. Then the last bit of testing is our track testing. I only got one slide about it because it's the bit that I've been least involved with. It's also the bit we do the least of because, you know, as I said, we do 225 runs of CFD every week for different things in the wind tunnel every week. The track, we only test maybe a couple of things every race. So what do we have there? We got our load cells on the car, so we know what loads go through the suspension. So we also know what downforce we get in certain places. We've got temperature sensors all over the car. That's to correlate with the CFD, but it's also to keep an eye on things, because if you know you get these silly things like a plastic bag gets cut up in the front brake duct, and you're going to be able to stop the driver and get that plastic out before the whole car burns down. So we keep an eye on things as well. We got pressure tappings, which are tiny little holes everywhere on the car, so we can see the pressure actually there, the suction we create, get a downforce. We got these wake brakes, so it's a bit of a truss structure, and you can see all these little circles, they're probes, and they're measuring the airflows. In this case, you can see the wake behind the front wheel. So for example, we would test 2 different front wings with that rake on and see if that's working well and how that correlates to our other tools. And then we've got the good old Flowbus paint. So that's just showing the health of the surface flow. And it's quite a good tool to use quickly. Obviously, if anything happens 20 mil away from the surface, you can't always tell from the flow of this. So it's quite limiting. You can only see what's happening on the surface. This is our ops room. So this is not at the track. This is at our factory in Enstone. That's where quite a few engineers are to keep an eye on things at the track as well. So you get all the data live from the track and you can do all your analysis. I spent 2 seasons in it as well to keep an eye on the aerodynamics. Anytime the car runs the track, that's full with people keeping an eye on things. Okay, and then the last bit that I like to mention is kind of the driver psychology, because it's not just about peak aerodynamics. You say it's actually quite easy to create a car that has a lot of peak downforce. But if it's not a stable platform, if it's not predictable to the driver, and if it doesn't comply with the driver wishes, he can lose half a second to a second a lap. You can imagine if you know you're going on the limit into the corner with this car, and lap to lap, it behaves slightly differently in that corner. You're not going to go full out. You're going to hold back a little bit because you don't know what the car is going to do. And that costs a lot of lap time as well. So actually, it's even more complicated in that you need a very stable platform that also has a lot of downforce on. And only then you get champagne and Sunday. Okay, as I said, the last bit. Sorry. I always get the question a bit, how did you get into F1? And the other question is, what does a typical day for you look like at work? So I thought I'll preempt those with a bit of information. So first, my journey into F1. Well, I'm Dutch. I grew up in the Netherlands, and my dad got me into Formula One. Absolutely loved it from kind of maybe 12, 13 years old, particularly the technological side behind it, because I love sports, but this is a combination of sports and technology. So got me really excited. I did science and maths. I loved the applied science, and I had a dream. Probably from I was 14 years old, I want to be an aerodynamicist in Formula One. That's not that easy to achieve. But still, I thought I'll give it a go. So I'll study aerospace engineering at the only university in the Netherlands that does aerospace engineering. Because even if that dream doesn't come true, I still got a good degree and I still have a good job at the end waiting for me. And that's where I think also, if you want to get into F1, that's not enough, an aerospace degree. So when we put a job description out for a junior aerodynamicist, you get hundreds and hundreds of applications. So you need to stand out a little bit. You need to have something different. And during my studies, I got involved with Formula Students. So that's these little cars here. So similar to Formula One, we would make a new car every year with about 60 people next to our studies. And as you can see, well, when I was there, it wasn't that much aerodynamics, but there's definitely a lot of aerodynamics involved now. And so there's big similarities there, and you would go racing with them in the summer. So that was a big plus. And also, I got connections at the university via Formula Student, and I heard that the university wanted to set up an internship with Ferrari road cars. So I jumped on that bandwagon, and I went to do my master thesis and my internship at Ferrari in Maranello. And that really, those things made me stand out, which meant that when I applied at every single Formula One team, 3 of them interviewed me. And in the end, I got a job at Renault in 2010 and moved up the ranks there by senior aerodynamicist, project leader on the nose. I was responsible for those ugly noses around that time, some of you might remember. And now I'm a deputy principal aerodynamics, and I look after the front wing and the nose of our car. So I'm based in Enstone. I don't really go to the track. I was lucky enough to go last year to the testing, hence the picture, but normally you can just find me in Enstone. And I manage a group of aeros there, aerodynamicist, and typical middle management position. I get pulled in all directions because I'm the kind of technical lead on the front wing. So if anybody has a question front wing related, they'll come to me. So I collaborate with the other group, but also with composites and strat. We need to make sure that any crazy idea we come up with can actually make it to the track, because in CFD it can just float in mid-air and be ultra thin, but that's not always you can't get that to the track. I manage the resource on front wing and the wind tunnel test programs, things like that. So what does a typical day for me look like? Well, it's not always a typical day because we run the wind tunnel kind of 5 days a week. So there's always surprises. Then there's the track testing. So when you get to work on Monday, you always get, a surprise from the track as well. But I thought this is kind of a typical day for me. So start the morning, catching up on emails and messages, as probably most people do in the job. Then I check in with my group, how they're doing, and make sure that everything is okay there. And a lot of it is fighting fires, because as I said, there's always surprises, there's always new information that needs quickly sorting. We don't have a lot of patience in Formula One, so it needs to be sorted now. From 10 to 11, it's planning meetings, but also a quick catch up with senior management about the latest results. And then I said, if I'm lucky, then before lunchtime, I get to see my own CFD results. That's a good day if I get time for that. But quite often I get caught up in meetings. And then at lunchtime, you find me in the gym. That's where I like to get away from my desk. My desk is over here. I'm almost in the picture. And then I always kind of keep some time for report reading and things like that, just after lunch. The afternoon is many more meetings, follow up from meetings, collaborating with others about aero development. And then the last part of the day is the kind of calm bit. That's when I get to do my own CFD development. So if I'm lucky, I get to see my results before lunchtime. So in the gym, I can already think about what should I do differently, what I'm going to do. And then the last bit of the day is actually applying that, sending them to our computer. And then the next day, it will start again.
Fantastic.
Thank you very much.
So just please thank our speaker once more for a great evening. A very